welcome to Grablo. In this tutorial, we'll build a person-following robot using AI object detection. The robot will automatically track and follow people using computer vision, adjusting its wheel speeds with PI control to move smoothly and naturally. Let's get started. Create a new project and add a new logic. First, let's create a control to start the camera and detect people. Since the camera only needs to start once when the project begins, add a once type condition. Next, add an AI camera action. Click Select and create a new camera. For this tutorial, we're using just one camera, so enter 0 for the index number. A resolution of 640 by 480 is sufficient. For orientation, select horizontal flip. Cameras naturally reverse left and right, so applying this flip creates a mirror-like view that's much more intuitive. When you move left, you appear left on screen, preventing confusion later. Select the camera we just created and click the Add button in AI Analysis. First things first, we need to know if there's a person in the frame at all, right? Set analysis type to object detection and command to specific object detected. For the object type, select person. Create a variable to store whether a person is detected and assign it. Next, let's add another AI analysis to get the person's center X coordinate. Again, select object detection and set the command to get specific object. For the object type, select person. Since there might be multiple people, set select by to largest size to track only the person occupying the largest area on screen. Click the select button for center point X and create a new variable to store this coordinate. Perfect. Now, while the camera is running, whether a person exists and the person's center X coordinate are continuously stored in our assigned variables. Pretty simple, right? Now let's add a control to measure distance using a distance sensor, so our robot doesn't crash into walls or other objects. Since we need to measure distance constantly, add an always type condition. Then add an I/O device control action. Click Select and create a new device. Grablo supports various distance sensors. For this tutorial, we're using the HCSR04P, which works with both 3.3 volts and 5 volts, making it safe for Raspberry Pi. Of course, you can use other distance sensors too. Enter the GPIO pin numbers where your sensor is connected and select the device we just added. Set the command to read distance, create a new variable to store the distance value, and assign it. Now comes the most important part, making the robot move forward and turn. For this tutorial, we're using an inexpensive RC kart kit originally designed for Arduino. It has no steering servo, so we'll need to turn by creating speed differences between the left and right wheels. We only want to move the wheels when a person is detected, so add a compare condition and select the person detected variable. Set the operator to equal and value to true. We also need to prevent collisions, so the wheels should only rotate when the distance is above a certain threshold. Add another compare condition and select the distance variable. Set the operator to greater than and value to 30 centimeters. Basically, when a person is detected on camera, the robot moves forward to follow them, but we need to adjust the rotation speed of each wheel based on the person's position to change the robot's direction. For example, to turn right, the left wheel speeds up by 10% while the right wheel slows down by 10%. Let's calculate how much to speed up or slow down each wheel. Unfortunately, we need a bit of math here. Add a set variable action and create a new variable called speed correction. Also create two more variables that we'll use in our formula. error and accumulated error. Select the speed correction variable. Launch the block editor to enter the value. To make the robot follow people smoothly, we'll use a control method called PI control. First, subtract 320, which is the screen's center X coordinate, from the person's center X coordinate and store this in the error variable. As the person moves right, this error increases, and as they move left, it decreases. This value is the error used in P, or proportional, control. Next, in the accumulated error variable, continuously add the error value multiplied by 0.05. We multiply by 0.05 because this is our time interval. Our logic runs every 50 milliseconds, or 0.05 seconds. This creates a mathematically correct integral calculation that accumulates how far off-center the person has been over time. Finally, multiply error by 0.06 and multiply accumulated error by 0.06. Add these two values together and connect them to the return block. We call the first 0.06 the P gain and the second 0.06 the I gain. Notice that both gains are equal in this case. These gain values aren't fixed and can vary depending on your environment. Start with these values and adjust through testing to find the optimal gains. Now let's actually control the wheel rotation speeds based on the speed correction we just calculated. Let's start with the left wheel. Add an I/O device control action and click Select. Create a new device. Since we're using a Raspberry Pi as our controller in this tutorial, select the Raspberry Pi DC motor library. Choose your motor driver type and enter the GPIO pin numbers where the driver is connected. Select the device we just added and set the command to run. Since DC motors don't have polarity, you'll need to test the actual rotation and change rotation direction to true or false so the wheel rotates in the forward direction. Now launch the block editor to enter the rotation speed. Set the rotation speed to 70 minus speed correction, constrained between 40 and 100. When the person is on the left, it rotates faster than 70%. When they're on the right, it rotates slower than 70%. Now let's calculate the right wheel speed. Duplicate the left wheel action we just created and add a right wheel motor device. Similarly, enter the motor driver type and connected GPIO pin numbers, then select the device. Set the rotation direction to true or false so the wheel moves forward, then click Edit Block for rotation speed to launch the block editor. Change the operator from minus to plus. This way, the right wheel rotates slower than 70% when the person is left of center, and faster than 70% when they're right of center. Now let's create a control to stop both motors. We need to stop when no person is detected or when the distance to an object is less than 30 centimeters. Instead of writing the conditions directly, since this is the opposite of our earlier control, add a watch condition. Select the wheel speed control that contains the conditions we want to reference. Since we need the opposite condition, set the option to invert. Now let's stop both wheels. Duplicate the left motor action we created earlier and drag and drop it into this control. Edit it and change the command to coast stop. Duplicate this action again and change it to the right motor. Both motors will now stop. One more thing we need. When the motors stop, we should reset the accumulated error value to 0. If we don't, when a person is detected again, this remaining value could cause the speed correction to calculate incorrectly. Add a set variable action, select the accumulated error variable, and set the value to 0. Great! Our logic is complete. Let's review what we've built. When the project starts, We initialize the camera once with horizontal flip enabled for intuitive viewing and continuously store whether a person exists and their x-coordinate in the background. We also continuously measure distance to objects using the distance sensor. When a person exists and the distance is greater than 30 centimeters, we calculate speed correction based on the person's position and adjust both wheel rotation speeds to keep the person centered in the camera as the robot turns. When no person is detected or the distance to an object is less than 30 centimeters, we immediately stop both motors and reset the accumulated error to 0. The PI control part was a bit challenging, but implementing it with just a few blocks is pretty amazing, right? If needed, you can also add a dashboard to monitor the camera feed in real time, person detection status, measured distance, error values, and more. The dashboard is optional, so feel free to skip it if you don't need it. Now let's connect the hardware. As shown in the connection table, connect each component horizontally to each other. One important point: power the Raspberry Pi with a smartphone power bank and power the L298N motor driver with two 18,650 batteries connected in series. They must use separate power supplies, but remember to connect the GND lines together. You can use either a Raspberry Pi camera or a USB camera. Both work perfectly. The HCSR04P distance sensor must be connected to 3.3 volts. Connecting it to 5 volts can damage the Raspberry Pi's GPIO pins, so be careful. All right, everything's ready. Enter your Raspberry Pi's IP address to connect. And click the Run button to launch the project. Let's test it by moving in straight lines, circles, and zigzags to see if it follows you properly. How about that? It follows smoothly, right? And when the distance to the person becomes less than 30 centimeters, it automatically stops. Implementing this with no code is pretty amazing, isn't it? Congratulations! You've successfully built your Grablo project. Ready to explore more? Check the links for tutorials and support. Thanks for watching and enjoy creating with Grablo.